At a sand and gravel plant, gravel is falling off a conveyor belt into a conical pile at a rate of 11.3 feet cubed per minute. The diameter of the base of the cone is approximately 4 times the altitude. And so this here, this is the oops, well, it's sort of in the right spot. There we go. There's our diameter. There's the altitude, or height, of the cone. And the important relationship there is that the diameter is 4 times the altitude. Let's put H. So if the diameter is 4 times the height is 1/4 of the diameter. That'll be an important relationship when we're working with this particular problem because it's got 3 variables. When the pile is 5.3 feet high, determine the following. At what rate is the height of the pile changing, and at what rate is the radius of the pile changing? Right, so let us first solve for the rate the height is changing. Right, we've done some problems like this with the volume of a cone. This one, though, instead of a tank where we're filling up, sorry, my microphone is tangled. I'm trying to untangle so I can move. We're dumping sand, and it's creating this pile here. And if you do dump sand, it does make a cone-shaped pile. Right, so let's look at our variables. Right, so we have, of course, we have volume. We have R for the radius, and H for the height of the cone, which of course is the inside measurement. Right, everything is changing. Right, as the volume changes, the height changes, the radius changes. It gets wider at the base and more narrow at top. All right, so all of our variables are changing. Let's look at our rates. All right, so we have dV dt, and that is 11.3 cubic feet per minute. And we want to find dH dt. All right, so we have this relationship here. We're given the height when the height is 5.3 feet. All right, so 5.3 feet is when we're going to find the rate of change in the height. So we have diameters for heights. So we don't usually use the diameter in the formula for a volume of a cone. It'd be 1/3 pi r squared h. So if the diameter is 4 times the height, the radius is 2 times the height because the radius is half a diameter. So now let's replace r with 2h. So we have volume equals 1/3 pi 2h squared times h. Let's simplify that. So that's going to be 1/3 pi, and that'll be 4h squared times h. And so if we combine like terms, we've got 4/3 pi h cubed. And now we'll take the derivative, right? So all of that part was just the simplifying. Let's take the derivative over here because I'm running out of space. So volume equals 4/3 pi h cubed. All right, so this is going to be dV dt equals 4/3 times 3. That's nice simplifying there. And then pi h squared. And then dH dt. Right, so just using the power rule, the 3 moves in front. We reduce the exponent by 1. Those 3's will cancel. So dV dt equals 4 pi h squared dH dt. Right, and so we want to solve for dH dt. So we have dV dt divided by 4 pi h squared will be dH dt. And this is not going to be a pretty number. Matter of fact, the fact that it's not a pretty number is going to influence what we do on B. All right, but let's just plug in our values and simplify. And since I've got some space over here, let's just do it over here. So we have dv dt, that was 11.3 divided by 4 pi and then 5.3 squared. Is dh dt. So let me just write it actually. I'm going to put the dh dt first. I'm just going to grab a calculator real quick, and then we're going to leave this in terms of pi. And so we've got 5.3 squared times 4, and then 11.3 divided by that, which is a very long, unwieldy decimal there. So I got, and you know what, I may as well divide by pi. I already have a decimal, so we'll divide by pi. So our answer is 0.03201. We'll put one more decimal place in there too. And that is feet per minute. All right, so now I'm going to write that on there. So 0.032012, oh, that's dh dt. Feet per minute. Right? Not a very pretty number. Right, but that's how the rate, that's the change in height at exactly when the cone is exactly 5.3 feet high. That is how the height is changing. Right? So let's take this problem. I'm just going to clone this page so I don't have to write that rate again. And let's do the second half on the next page, where we have a little bit of space. All right, so I'm going to keep the relationship up. I'm going to erase dh dt. It was on the last page. I'm going to erase all of this. And we're no longer looking for dh dt. We have dh dt. It's right over there. You can write it again, I guess. dh dt is 0.032012 feet per minute. And it is rounded. So it does create rounding error to use that. So now we want to find the rate of change in the radius of the pile. Same time, 5.3 feet. Now, first of all, we need to know when the height is 5.3 feet, what is the radius? Okay? Well, the radius is twice the height. So it's going to be 10.6 feet. So again, we have the equation. Oh, and we're looking for a dr dt. We have the equation volume equals 1/3 pi r squared height. We now have, we have dh dt. We're looking for dr dt. We have dv dt. We could just use the product rule, find the derivative, and plug in all the rates. However, we rounded dh dt, right? It had a pi in it. It was a non-terminating decimal. I'm a little hesitant to use that rounded value. Plus, we have to use, the derivative will be harder. And we have a relationship between the radius and the height. So just because we could use the product rule here and plug in all the rates, rather than working with a more difficult derivative, it might make more sense, and a rounded value, it might make more sense to go right back to that same relationship, rewrite it so there's no height in the equation, and work with it that way, even though we could use the dh dt. And having done a few problems where I did not rewrite it and I went with the product rule, I'm going to say it will probably be much easier in this situation to just rewrite the equation. So let's do that. All right, so now we want to replace the height since we want dr dt, and right here we have our relationship. So the height is 1/4 of the diameter. Now we're not going to use, of course, diameter, we're going to use the radius. So if the radius is 2 heights, then 1/2 of divide both sides by 2, right? And the radius divided by 2 will be the height. So now this is the one we'll use, right? Because we're not going to work with diameter in that equation anyway. So we're going to replace the h with r over 2. And then we don't have to worry about using that crummy dh dt value. So we have volume equals 1/3 pi, and then r squared times r divided by 2. So we can just combine the 3 and the 2. So that's going to be volume is 1/6 pi r cubed. All right, and now let's take the derivative. And I'm going to move this over just a tad. Oops, not the picture. This. So I can use the space. Oops. Not the picture, I said. One more try. There we go. All right, so now let's take the derivative over here. So we have dv dt equals 1/6 pi times 3, and then r, now it's r squared, right? So that's going to simplify nicely. So dv dt equals, and so that's now going to be 1/2 pi r squared. Oops, dr dt. Oops, forgot the dr dt. I ran out of space and just stopped writing. dr dt. Right, because this is with respect to time. All right, so now we need to simplify that. So we'll multiply both sides by 2 so that we have 2 dv dt, and then divide by pi r squared, and that will give us dr dt. So now let's plug in and see what we get. All right, I have no idea where I'm doing the plug-in. I guess over here. So dr dt is 2 times 11.3 divided by pi, and then the radius we got was 10.6 squared. And now I'm just going to give you the decimal equivalent. I'm not going to even make it in terms of pi. What's the point? We already have to round for the those values anyhow. So we have 11.3 times 2, and we'll divide that by 10.6 pi. And we get 0.6788661, and that's feet per minute. And there we go. So just because we could have used the dh dt doesn't mean we necessarily should use the dh dt. If it's going to give us a more difficult problem to solve, it's going to create rounding error, why not go with an easier method? So we have the relationship, and I'm all for using that relationship. Well, that's the end of this video. We're going to look at one more concept related with related rates, one more type of problem, and we'll look at shadows. Thanks for watching. Bye for now.